Hello, this is our second class on the introductory lectures of formal languages and automated theory. So today I will give you the more formal introduction to the theory of languages and machines. So maybe today's topic may be headed like this: strings and languages. So I make a small recapitulation from the previous lecture. So we represented sets, which are called languages, of several useful things like numbers, graphs, sequences. Numbers may be integers, some other things, maybe graphs, polynomials, and so on. Okay, so each such thing we demanded should have a finite representation, and each such representation can be encoded as a string over some alphabet. I will define strings formally. And what is more important is that only the two symbols, let's say 0 and 1, suffice for all finite encodings. As strings. Okay, so given this understanding, we are now ready to formally define strings and languages. So I start with the definition of strings, or maybe a string is defined over something called an alphabet. This is defined as a finite set of symbols. So it's important to note that we demand this to be finite, and the elements are called symbols. You may also call them letters, but the elements of an alphabet cannot be called alphabets themselves. Okay. So these are basically the symbols from which or of which the strings will be composed. So let me give a few examples. As we have already mentioned, we typically consider the set 0, 1 as the binary alphabet. And then you may think about alphabet of decimal digits So it consists of this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you may additionally add these two signs, plus and minus, to represent, for example, signed integers. Also, you may add a decimal point or a binary point to represent floating point numbers. Or real numbers. Anyway, so these are examples of two alphabets. You may also think about the Ascii alphabet. And that consists of printable characters, possibly some non-printable ones too. You may also consider this Roman alphabet, consisting of the lowercase letters A, B to Z, uppercase letters things like that. And you may also think about this alphabet for English language. That consists of, first of all, the lowercase letters, uppercase letters, also you have this 0, 1, 2, 9, the digits, and you may also add the punctuation symbols. And of course we need another thing, space. So this is a space or blank. Sometimes we write it as this in order to understand it's a space, or maybe sometimes like blank, whatever. So alphabets are finite sets of symbols, and we use these symbols to define strings. So in this course we will use uppercase Greek letters like sigma, gamma, delta to stand for alphabets. And their individual symbols, they may be represented like lowercase English letters, A, B, C, like that. We may also use 0, 1, 2, things like that. So this is kind of notation that I want to introduce. Okay. We will use typically these three symbols, sigma, gamma, and delta to stand for alphabets, and English letters near the beginning of the alphabet, Roman alphabet, A, B, C, D, things like that. Also sometimes 0, 1, 2, these digits to stand for symbols. I mentioned earlier that this alphabet suffices for all representation purposes. But in order to be more general and to work with more, I would say, variety of problems, we may often go to a general alphabet. For example, if we talk about integers in the decimal representation, this alphabet 0, 1, 2 up to 9 may be more useful, although binary encoding makes only these two symbols 0 and 1 suffice. Anyway, we will be more general to define alphabet this way. Now comes an important thing, a string. Whenever I talk about a string, I always assume that its symbols are coming from some alphabet sigma. And if that is the case, we will call this as a string over the alphabet sigma. This is a finite, this is important, a finite sequence of symbols from sigma. So by definition, a string is a finite sequence. Also, this finite means infinite sequences are not classified, or they do not qualify as strings. And sequence means these are ordered, these are not sets. So it talks about, it makes sense to talk about the first element, the second element, the third element, fourth element, and so on. Okay. For example, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. This is a binary string, that is a string over the alphabet 0, 1. You can also talk about things like A, B, R, A. This is a string over the Roman alphabet, and so on. Okay, so look at this. This is not a set. This is a sequence. So A appears multiple times. So let it appear. So this is not same as collapsing all A's or neglecting the orders. This is not like that. This is a string. Okay, the entire thing. The first element is A, second element is B, or second symbol is B, third symbol is R, fourth symbol is again A. Okay, and so on. And again, we will usually use U, V, W, X, Y, Z. The English letters near the end of the Roman alphabet to represent strings. And we may also use things like alpha, beta, gamma. Okay. Lowercase Greek letters. Okay. So this symbols like A, B, C near the beginning of the Roman alphabet will typically be used to denote symbols, whereas those near the end of the English alphabet are typically used to represent strings rather than individual symbols. And also we may use lowercase Greek letters. Okay. Yeah. So this is how a string is formally defined. Now, this is an important thing. Length of a string is the number of symbols in it. For example, the length of this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So counting repetitions, total number of symbols. So the length of W is typically denoted as this. Okay. Now there is one string which is of concern. This is the string of length 0. Of course, in C you like something like this. Okay. But here we do not actually use this quotes to denote strings. Okay. So we use the special symbol epsilon to denote the empty string. There is a unique string of length 0 over every alphabet. This is called the empty string. Okay. Okay. Now, given sigma, an input alphabet, we denote by sigma star the set of all strings over sigma. So this star operation we will use for a variety of other reasons, and the later uses we will see these are quite consistent with this notation that I introduce here. So for example, if I have sigma equal to A, B, C, this 3 symbol alphabet, then sigma star consists of these strings, the string of length 0, 3 strings of length 1, 9 strings of length 2, these are the things, CA, CB, CC, and then we have 27 strings of length 3 and so on. Okay. So this is sigma star. Okay. Okay. Fine. I will also denote for a symbol A in some alphabet this, I will denote A power n as the n-fold concatenation of A. Okay. And by convention, what is the 0-fold concatenation? This is epsilon. Okay. So A appears 0 times. So this is the null string or the empty string. Okay, so the empty string is also called the null string. And you can see that the sigma star supports an operation called concatenation. So if X is a string and Y is a string, so if for example X is something like A1, A2, AM, Y is a string B1, B2, Bn, where each AI and each Bj is a symbol over the underlying alphabet. Their concatenation typically written as XY. This is the symbols of X followed by the symbols of Y. Okay. So this concatenation operation we will often use in connection with strings. An important thing about concatenation is that this operator is first of all closed. Okay, if you concatenate two strings, there are two finite sequences. You write one sequence followed by the other, you will get yet another finite sequence over the same alphabet, and therefore it is a string. It is clearly associative. It is not necessarily commutative. For example, the concatenation of AB and BA as a string, this is not the same as the concatenation of BA and AB. This is AB BA, this is BA AB. So in general, commutativity does not hold for the concatenation operation. But this epsilon, the null string, acts as the identity. That means if you take any string W, concatenate it with epsilon, this direction or this direction, you will get W. And we have seen many of the axioms of a group, but we do not have a concept of inverse. Okay, so an operation or a set with these three properties holding: closure, associativity, and existence of an identity. This need not hold, this need not hold. This is no longer a group because it does not have inverses for elements. So this is called a monoid. Whatever it is, not very important thing. So sigma star is a monoid under the operation of concatenation. Okay. Good. So it's an important operation. We will come to this operation quite frequently in throughout the rest of this course. But now, in order to define languages, we use strings. Okay, so we no longer talk about a language of numbers, language of graphs, language of things like that. We will simply call them languages. So a language over an alphabet, over an alphabet, sigma is any subset of the set of all strings. So it consists of strings. So it's a subset of sigma star. Okay. So L, we will use L, L1, L2, things like that. Sometimes maybe we use AB, capital AB. So this uppercase English letters. L or towards the beginning of the Roman alphabet, uppercase alphabet. So these notations will be used to represent languages. Okay. So languages are sets. They are sets of strings. Okay. So these are our formal definitions. So because every interesting thing can be encoded as strings, so these strings may stand for a lot of things. They may stand for numbers, they may stand for graphs, they may stand for polynomials, and so on. Okay. So we will no longer classify the strings as strings coming from integers or floating point numbers or graphs or whatever. We will simply deal with strings. Depending upon the application, the strings will mean different things. Okay. Now, I once again come to the question of I once again raise the question of countability versus uncountability. Okay. So sigma, to start with, is a finite alphabet. Incidentally, what I forgot to mention, we usually do not consider the empty set as an alphabet. Okay. So maybe if I go to some previous slide, maybe it is here. Where did I define an alphabet? It's here. Yes. So it's not only finite, just we should also write something called a non-empty finite set. Okay. Empty sets are not good for representing things. Okay. Anyway, so the sigma is a finite alphabet. We may even have sigma equal to 1. It's a unary alphabet. But it is at least 1. The empty set is not considered as an alphabet because there are no symbols in it. Sigma star, the set of all strings, is countable. Why? Because there are finitely many, and in particular, whatever the size of sigma whole power n strings of length n. And n can be anything between 0, 1, among 0, 1, 2, 3 and so on. So sigma star is nothing but a countable union of countable, actually finite sets. And we have proved in the discrete structures course that such a set has to be countable. Whereas, if I consider a language L, it is a subset of L. And therefore, I can say that the set of all languages over sigma is nothing but the power set of sigma star. Or you can write it like this, 2 power sigma star. And by the power set theorem, this set cannot be in bijection with the countable set sigma star. So this is uncountable. Okay. So this is an important thing. Sigma star, each string is a finite sequence, but if we consider the set of all such finite sequences, that is set of all such strings, it is a countable. But now if I look at all possible subsets of sigma star, that is all possible languages, that set is now uncountable. Okay. And okay, so strings now, of course, the next question. So this is an important thing, just keep it in mind. The set of all languages is uncountable. Okay, so I will go to next slide. So the next question, representation. First, strings. So they are after all finite sequences. So there is no problem in writing down a string explicitly. Okay, a very long string will take a very long space, but it is finite after all. But languages may consist of only finitely many strings. They may also consist of an infinite number of strings. For example, sigma star itself is a language. It is the entire sigma star, and it is infinite. So if we are dealing with a finite language, we can have an explicit enumeration. Okay. If there are n strings, w1, w2, w3 up to wn, then we can simply write w1 followed by w2, w3 and so on, wn. If n is a finite thing and each string is by definition finite, so this entire representation takes only a finite amount of space. So the problem comes when we are dealing with infinite sets. Okay, so we have already come across such infinite sets of integers. So now we can no longer explicitly write down all the elements of the language. So this is no longer possible because it will take an infinite amount of space. So languages, particularly the infinite ones, need some other mechanism for being represented in a finite amount of space. Okay. So particularly these infinite ones require finite descriptions. And we have seen quite a few examples in the first lecture. So this can be done, for example, in an English-like language. Like the set of all strings over some alphabet of, let's say, even length. So this is an English language description. We may also have a mathematical description. For example, we may have set of all w in 0, 1 star, such that if you treat W in binary, so it's now a number, W is a multiple of 3. Things like this. There are other ways also. Anyway, okay, mathematical description. Then we may often have something like a recursive description. For example, let us say all palindromes over A comma B. So how do you define a palindrome? So it's a string that reads the same forward and backward. So you start from a core, center, which may be empty, which may be a single symbol A, and then single symbol B. And then starting from the core, here you add symbol 1 and the same symbol here. Then you add symbol 2 here, add the same symbol 2 here, and so on. Finally have symbol N here, the same symbol appearing here. So this is a kind of recursive definition for palindromes. Okay. And the final thing, which we have not come across so far, actually, recursive description. So this often includes what is called grammars. Okay. So we'll look at more specific instances of grammars later. For example, for the moment you may think about English grammar. I will come to that little later. You may also have description by procedures or machines. Near the end of today's talk, I will briefly highlight or briefly explain what is meant by illustration, by the description of a language by a machine. Okay. So let's not, I would say, worry too much about these things. In fact, the rest of the course is devoted to representing languages using machines and grammars. Okay. We will eventually develop our ability to describe different types of machines or different types of grammars to address different types of languages. Today I will give a very brief description, but the rest of the course is anyway devoted to an in-depth study of all these things. Okay. What I want to highlight here is that, so we are talking about languages over some alphabet sigma. And the description of a language should be finite. In whatever fashion we use it. Mathematical symbol, as a machine, as a grammar, as an English language description, it should be finite. We cannot have an infinitely long description of a language. For example, the exhaustive enumeration is not called a description, a finite description for an infinite language. So it should be finite. But this description also uses some alphabet, maybe the English alphabet, the alphabet of mathematical symbols, blah blah blah, like English a Roman alphabet. It may be alphabet of mathematical symbols, and so on. So we call this alphabet, the representation alphabet, gamma. And since this description is a finite description, okay, so this description must be itself a string over gamma. Okay, so once again I assume that gamma is finite and non-empty, of course. Okay, so given that description of a string over this gamma is a string over sigma, okay, so a language over sigma is represented by a string over gamma. So the valid descriptions are nothing but elements of gamma star, right? And we know that if gamma is finite or even countable, gamma star is countable. Okay. Whereas, compare this with set of all languages, which is P of sigma star. This is uncountable. Okay. So the implication of these two, I would say, facts is that only countably many languages can have finite descriptions. And this means actually an uncountable number of, that is, most of the languages cannot be described in a finite amount of space. Okay. Now, these two things imply a very important concept related to computational problems. Okay, so given L, a language over the alphabet sigma, and some string W in sigma star, decide whether W is in L or not. Okay, so this is computational problem defined in the most formal way. So a computational problem by this is nothing but a decision problem. And it may seem a little bit loss of generality for the moment, but it is actually not exactly so. So this definition, I would say, is good for all theoretical I would say, developments. And not only that, as I mentioned, they have stood the test of time. Defining things this way does not harm us in arriving at important results about computability. Okay, but given this, L is a language over sigma. So, how many computational problems are there? There are as many languages. It's basically nothing but the language membership problem. It's like checking whether some number is a Fibonacci number, whether some graph is connected, whether a number is a happy number or an unhappy number, things like that. Okay, this is a language membership problem. But since there are uncountably many languages, I can say that there are uncountably many problems, because problems are identified with languages. So problem are same as languages under this formal definition, because a problem is nothing but a language membership problem. Okay. And since there are uncountably many languages, there are uncountably many problems. But whatever way we specify a problem using a machine or in English language or whatever way, we can have only countably many finite descriptions, which includes machines. We will not call them machines. We will soon call them automata, to solve problems. Okay, because we can have only countably many machines with finite descriptions. Okay, so that implies there are many, in fact uncountably many, unsolvable problems. And proving things to be unsolvable is not really very easy. We will do near the end of this course. Okay. But it is important to note that it is difficult to find such problems which are unsolvable. It is like finding transcendental numbers like pi or e. It requires quite some effort to prove their transcendence. Okay. Moreover, proving unsolvability is also a serious issue. Okay. In order to prove that certain thing is solvable, just build a machine for it. Okay. In order to prove that something is not solvable, you have to somehow prove that no machine works for this. And this kind of proofs are significantly more involved than designing machines. Anyway, we will look at something like diagonalization proofs, similar to the diagonalization proof you have seen in the discrete structures course, for proving certain unsolvability questions. And then we will use another very important technique called reduction for proving further unsolvability results. Anyway, those are all topics of the future. I believe we are now happy with the broad outline. So let us look at a few things like so we have these things. So strings and sets of strings, which are called languages, these will play a vital role, or the most significant role, throughout the rest of this course. So it is a good thing to talk about some elementary properties of these things. So operations on strings. Okay, so for example, we have already defined an operator called concatenation. Okay. Already defined, so I am not coming to that. Concatenation of string 1 with string 2 is write string 1 followed by string 2. Concatenation allows us to define something called powers. Okay, so Wn, okay, n greater than equal to 0. So I can define it this way, given that we have defined concatenation. This is the empty string. If n is 0, irrespective of whether w itself is empty or non-empty, and then we define w concatenated with wn minus 1 if n is greater than equal to 1. Okay, so for example, if I have this string 0, 1, this whole power, let's 3, take a specific value. This is 0, 1, 0, 1, 0, 1. And this has to be distinguished from this. This means 0, 1, 1, 1. And this is also a different thing. 0 cube, 1 cube is nothing but 0, 0, 0, 0 3 times, 1 3 times. Okay. So these notations we will use frequently to denote powers of a string. Okay. So W is a string, so it's an n-fold concatenation of W with itself. Okay. Okay, and the 0th power is always assumed to be the empty string. So keep this thing in mind, and prefix is another operation, or a similar and analogous operation called suffix. Let W be a string over sigma. U in sigma star is called a prefix of W if W is the concatenation of U followed by V for some V in sigma star. Okay. Likewise, I can define suffix where only I have to use instead of this, I have to use, for suffix, I have to use VU. Okay. Okay. So this is how prefix is defined. It's just a formal definition, but if you, for example, look at all prefixes of, let's say, A, B, B, C, A are empty string A, AB, ABB, ABBC, and the entire string itself, and all suffixes of the same string ABBCA are epsilon A CA BCA BBCA and A BBCA. Okay, so these are often called proper suffixes, proper prefixes, and these are called proper suffixes. Anyway, possibly you already know about these suffixes and prefixes when you studied the Knuth-Morris-Pratt algorithm in your Algorithms 1 course. Anyway, so these are important operations and notations that we will use to work with strings. Now let us look at operations on languages. Okay, so languages are nothing but sets. In fact, when we fix the input alphabet sigma or the alphabet sigma, there's all subsets of sigma star. So this sigma star acts as the universal set when we talk about all languages over sigma. In particular, if we are given two languages A and B, we can anyway talk about their set theoretic union, because they are sets after all. They are set theoretic intersection. And we can also talk about the complement of A, written this way or this way, by a bar or complement. So this is nothing but sigma star minus A. Okay. So the sigma star here acts as my universal set, and complement is with respect to that universal set. Okay. And since they are sets, all the set theoretic identities hold. Right, like De Morgan's law, distributivity of union over intersection, intersection over union, all these things hold. Okay, and so on. So we do not need to, I would say, have any special treatment for this, but what is important, like strings, we can define concatenation of sets. So if A and B are two languages over sigma, the concatenation of A with B is defined as set of all strings of the form UV. So U comes from A and V comes from B. Okay. So take any element from this A, any string, any element from B, concatenate them. Okay. And whatever you get, that is the concatenation of this A and B as sets. For example, if A is my finite set A and AB, B is epsilon and B. What is AB? A epsilon is A, AB is B, AB epsilon is AB, AB B concatenation is this. Okay. something like this. And once we have this concatenation, we can also talk about powers. Okay, so let A be a language over sigma, then powers of n are defined as a power 0 and a concatenated with a n minus 1 if n is greater than equal to 1. Okay. This is fine, right? For example, if a is something like a and ab, what is a power 0? This is nothing but the empty string, set of the empty string. A power 1 is nothing but a. Concatenate this with this, you will get a, ab. What is a square? Okay, a concatenate with this, so ab, ab you concatenate with this and this, aba, ab, and so on. Okay, and a star, this is called the asterisk of a, or it is also called the clean star. This is another name for this asterisk. This is the union of a power n for all n greater than equal to 0. Sometimes we also define this a power n greater than equal to 1. And this is defined as n greater than equal to 0. Yeah. So, recall that we have defined sigma star. Given sigma is this. Now sigma itself is a language, right? Because 0 and 1 length 1 strings. Okay, maybe this alphabet. Sigma star is nothing but the empty set the square and so on. So with respect to this new definition of star and the old definition of sigma star, there is no problem. Okay, these are perfectly consistent. Okay, so this is a string of length 0, these are all strings of length 1, these are all strings of length 1, these are strings of length 2, strings of length 3, and so on. Okay, so power, and one important thing that I would like to mention here, a few identities about this asterisk. Easy to prove all these things. A star, concatenate a star with a star, you will get a star. If you take one asterisk and once again make an asterisk of that, you will get nothing new. It will be same as a star. And this empty set is also a language. But when I take asterisk of this will contain this. Okay, because this is true for any phi. And after that, phi 1 is nothing but phi, epsilon. So that is phi. Okay, and so on. So phi, phi square, phi cube, these are all epsilon, all empty. This epsilon is coming because of putting n equal to 0. I see. Okay. Okay. And also you can define, you can also see okay, so this is all identities follow from the definition, and you can try to prove these things. I am not going to the proofs. Okay, these are all immediate from the definitions. Okay, so that's about the algebra of languages. Standard set algebra, union, intersection, complement, and other things like symmetric difference, all these things. Whatever we use in connection with sets can also be used here. Now we have a special thing because strings support something called concatenation. So we also talk about concatenation of sets, from which we can define the asterisk, the cleanest star of sets. Sets of strings, that is, of languages. Okay. So these are just some notations. Before ending today's lecture, I give you a very brief introduction to description of languages by machines. From this point onward, let us not call machines as machines. They are called automata, and this is actually a plural. In singular, it is called an automaton. Sorry, automaton. Okay. Okay, so what we do, we always assume a machine has a finite control. So this is like the CPU. So a finite control typically consists of a finite set Q of states. Okay. And this finite control at any point of time can be in exactly one of these states in Q. Okay. Then a machine also requires some input. So the language recognition problem is nothing but L is a language. So this machine, okay, so this is a subset of sigma star, that is a language over sigma. So this machine represents L. Okay. Now, when I talk about L, so I have the corresponding language recognition problem like this. I am given a W in sigma star. Output is the decision. Accept if W is in L, or reject if W is not in L. Okay. So W should be presented to this machine, and it is typically done externally. So this W, input string. The machine reads the strings, okay, and eventually we can say that this machine comes with and does some computation, and we can say that the machine has two, I would say, maybe you call them two output indicators. Okay. So, do computation on W. Okay. And if it is found that W is in the language, then maybe the green lamp glows. And if W is not in L, the red lamp glows. And at that point of time, the machine either switches off this green light or the red light, and the machine or the automaton stops at this point. Okay. So this is the basic idea. So the input is presented externally, and you have a finite control with two output indicators, acceptance or rejection. So this is the basic model of an automaton. Okay. And different types of automatons are characterized by what external memory that machine has. Okay. So that means in addition to this and this input, it may have some external memory, something like this. So this is the finite control. This is the input. In addition, the machine may use this external memory for doing some rough calculations. Okay. So this external memory is something very, very vital, and they define different classes of automata. To start with, we will study finite automata. So they do not have any external memory at all. Whatever computation it has to do, it can use only the memory available in the set of states. Okay. Only so finite memory. So that is the finite control. Okay, it can remember certain things by being in particular states. Okay, but no external memory. Then we will study another class of automata called push-down automata. So it has an infinite external memory, but it's not a random access memory. This is organized and accessed as a stack. Okay, it's an infinite memory, but its organization is restricted as last in, first out access. Okay. Then we have something called linear bounded automata. So here the input tape is rewritable. There are no other external memory, but so this is the finite control, and this input is provided here, but you can overwrite this and do some scratch computations here in this part. Okay. In earlier cases for finite automata and for push-down automata, this input is assumed to be read-only, but now you can overwrite symbols and write things there, and this actually increases the language recognition power of these machines. These are called linear bounded automata, but they are actually space restricted. Whatever this machine wants to do, it has to do in the same space as provided for the input. No extra space. This is still some kind of external memory, but this is a finite amount of memory. But you can do anything there. Move back, forth, and write, erase. Okay. Anything you can do on this part of the tape or this part of the input. Finally, we will have here you have an infinite read-write tape. Okay, so it's something like this. There is a left, don't slip beyond that point. Initially the input is provided here, and then you have infinitely many empty cells. Okay. And input is typically provided at the beginning, except this point, which is the end marker for this thing. And this entire string entire tape can be traversed. Not entire thing, infinite number of cells cannot be traversed in a finite amount of time, but anywhere you can go in any finite location, read, write, overwrite, come back, and all these things. We will see that. And of course, you will have this finite control. This kind of read-write tapes, okay, will give the machine the ultimate power of recognizing any possible, I would say, languages as is possible. Okay, nothing better we can do. Okay. Anyway, I'll come to that. We will come to that near the end of this course. But this is basically the organization, a finite control. Input is provided somewhere, and then you have some external memory, which may be completely absent, which may be in the form of a stack or a read-write thing, the same space as the input, or something like this. Okay, for a Turing machine. Okay, you may think of other machines like infinite external memory associated, accessed, organized as a queue. All these things will happen. We will look at these things later. Okay, a queue machine and all that stuff. And so this type of machines we will eventually study. And alongside these machines, we will study another formalism Okay, so these are called grammars. They have equivalent descriptive powers as the machines. So finite automata they have one-to-one correspondence with what is called, or what are called, linear grammars. Then we have push-down automata. They have one-to-one correspondence with so-called context-free grammars. Then we have linear. I hope I have written it correctly. Let me see. No. Oops. Okay. Okay, fine. I have written correctly. Maybe I go here. Okay. Linear bounded automata. You will see that they correspond to what is called context sensitive grammars. Finally, Turing machines. They correspond to unrestricted grammars. So, these are machines. Finite automata, push-down automata, linear bounded automata, Turing machines, these are machines. Whereas these grammars are equivalent ways of specifying the same set of languages accepted by these machines. Okay. And so this is often called a type 0 grammar. So type 1, type 2, type 3 grammar. Okay. Anyway, these are different names. So I end this lecture by drawing a picture. So first of all, we have this set of finite languages. Okay. So these languages are actually called regular languages. These are called context-free languages. CF stands for context-free. These are called context-sensitive languages, coming from this, context-free, context-sensitive. This we will write a little bit later. So, then we have regular languages, which also consist of all finite languages. Then we have a bigger class called context-free languages. Then you have context-sensitive languages. This is called, maybe I write it here, recursive languages. Okay, so these are languages of Turing machines of a particular type. Beyond this, we also have something recursively enumerable languages. And outside this, there are languages which are not even recursively enumerable. So R is recursively. So we will make our journey by first understanding the regular languages, then the context-free languages, and we will not cover context-sensitive languages in great detail. Maybe 1 or 2 exercises will do it. Then we will talk about recursive and recursively enumerable language. And if I simply restrict our attention to this class, recursive languages, it is considered this class, everything inside this magenta region, this is called the I would say the region of a domain of computability. Beyond this, whatever problems are there, we do not call them computable. Anyway, so this is still a long way to go. I think this is already good enough as an introduction. Okay, so from the next class onward, we will start our study of regular languages and their different type of representations using finite automata or linear grammars. Maybe we will cover in some exercises. We will see another thing called expressions, regular expressions that can also define regular languages. Anyway, so we will start those things from the next class. And let me stop here. And so this is a brief course description and the definition and introduction of notations that we will follow for the rest of the course. Okay, from next class we will start the actual topic. See you by then. See you.